last week, we mainly discussed the concept of shape functions. So we basically said that displacement can be written in terms of shape functions. So the displacement u is equal to n1, n2 multiplied by u1 and u2. Now, we said that we derived the shape functions. So n1 is basically x minus, or it is x2 minus x divided by x2 minus x1. And n2 is equal to x minus x1 divided by x2 minus x1. So this is for an element. I'll just draw the element here. So this is for an element. This is node 1. This is node 2. u1 is the displacement at this node, and u2 is the displacement at this node. X is the axis moving in this direction, and the coordinates of x1 for u1 is x1. Is x1, oops, and is x2 here. All right, so we did a plot for the shape functions. So if we assume that this is the x, probably just make it a bit larger. If this is the x-axis and this is the y-axis, and you want to plot the shape functions n1 and n2, I will just be using colors for n1 and n2. So n1 would look like this. So the value of n1 is 1 at x1 and 0 at x2. So this is how the first shape function would look like. And the second shape function would look like this. So it is 1 at x2 and it is 0 at x1. Now, this can be, as we discussed last week, so this can be quite a powerful tool to be able to recover pretty much any type of displacement that are happening between node 1 and node 2. So let us assume that the displacement at node 1 is 5 and the displacement at node 2 is probably 2. Then in between, the displacement are varying in this way. And if you multiply n1, probably just write it here, n1 with 5 plus n2 multiplied with 2, you can recover exactly this line here. Just use a different color. So you can exactly recover this line here. If it is different, I probably go for something like this. So if the displacement is minus 5 to, I don't know, probably 4, then in this case, instead of 5 and 2, just multiply it with minus 5 and then 4, you can recover this line quite accurately. You actually recover exactly this line here. Oops. And you can do this pretty much for any line, or you can do this pretty much for any displacement, any field of displacement, as long as the displacement field is varying in a linear way. Now, if you look into the examples we have been solving so far, so if you look into the example of a cantilever constrained at one end and loaded with a load F at the free end, then in this case, the displacement is going to be U is equal to, at this end, of course, this is 0, U is equal to 0, this is fixed end. At the free end, the displacement is going to be basically the force. The displacement is actually proportional to the force and is proportional to the length. So the longer the beam, the larger the displacement is going to be, and it's going to be inversely proportional to the cross-section. So the thicker the cross-section is going to be, the smaller the displacement, and it's going to be inversely proportional to the elasticity modulus. So the higher the elasticity modulus, the stiffer the material is, the smaller the displacement is going to be. So it is proportional to F, proportional to L, inversely proportional to the cross-section and the elasticity model. So the displacement at this free end is going to be FL divided by E. A, this is the exact displacement I'm speaking here about, the exact displacement. And between 0 and 1, the displacement is going to vary in a linear way. So the displacement is going to increase linearly to get to this point. So this type of shape functions, N1 and N2, can recover this type of displacement exactly. They can recover it quite well. However, if we come to a situation where the force is increasing or changing in a linear way, or in a case, for example, we have a uniformly distributed force. So I'll probably just use black for that here. We have a uniformly distributed force. So this uniformly distributed force is small w or omega. Then in this case, the displacement is not going to change in a linear way. The displacement is going to change in a quadratic way. I mean, I probably can go into solving the problem exactly. I think it is probably a good idea to solve this problem exactly analytically before we get into the higher order type of displacement. So I'm going to probably define an x at this end. I think this would be probably the easiest way to solve this problem exactly. So right at the tip, you have 0 force applied, where the length is 0, basically. If you move in this direction, the force is going to increase as the value of x is increasing. So if you like, if you cut it at some section, at this section here where the length is x, you will have the force to be x multiplied with w. Now, if you are looking into the stress is the force divided by the cross-section. And since the force is x multiplied by w, so you will have the force to be xw divided by a, and this is the value for the stress. Now, if you want to find the strain, you just have the stress to be the elasticity modulus multiplied by the strain. So this way, the strain is going to be the stress divided by the elasticity modulus. So this number here, this quantity here divided by the elasticity modulus, you will have the strain. So the strain is going to be Wx divided by E and A. Now, how about the displacement? The relation between the strain and the displacement is just like the relation between the velocity, if you like, and the displacement. So the strain is basically the derivative of the displacement. So the strain would express the rate at which the stress, the rate at which this displacement is changing, just like the velocity and the displacement. So the rate at which the displacement changes is the velocity, and the same is correct, or the same type of relation is correct between the strain and the displacement. So basically, the displacement is the integral of the strain with respect to x. Now, this is correct when we talk about axial forces. If we talk about bending moment, or if we talk about shear, this is a different type of relation. That this is a second order derivative. But if we are talking about the axial forces, the relation between the strain resulting from the axial forces and the displacement is just the integral. As I said, pretty much the same like the displacement and the velocity type of relation. Now, I will integrate this quantity here with respect to x. I can find the displacement. So u is the integral of omega or w small x divided by ea dx. The integral of this with respect to x, only x is the variable here. This is a linear variable, so the integral is just going to be, this is constant, is not going to be related to the integral, multiplied with x squared divided by 2. Obviously, so this is an indefinite integral, so there is no boundaries or there's no limits for the integral, so you need to add a constant there. So plus c, a constant. Now this c would be defined based on the boundary conditions or based on the displacement that you know. If you look into the problem here, you know for sure, you know for certain that at the support, the displacement is equal to 0. So you just substitute that into your equation. And then you'd be able to find the exact equation for the displacement. So in this case, at x is equal to L, and be aware that x is starting, I've picked my x to start at this tip because this is easier for me. This is more convenient. Now, if you want to start it at this end, you need to add the reaction into the picture, which is going to make it a little bit more, just slightly more less, or probably just less convenient for you if you want. So I've picked x here because this is more convenient for me. And at this point, x is equal to L. And at this point, the displacement is equal to 0. So this is what I know, and this is what I'm going to use to define the displacement. So x is equal to L. This will give me u is equal to 0. And if u is equal to 0 at this point, I'm just going to substitute x equal to L, and I will find the value of c in there. All right. So 0 is going to be w e a multiplied by L squared divided by 2 added to c. And then this is possible if the value of c is equal to, I'm going to take this quantity to the left-hand side, and this will make it negative. So it is going to be w L squared divided by 2 e a. So this is obviously negative. So this is the value of c. I will put c back into this equation there, and I will find an exact expression for the displacement. So the exact expression for the displacement is going to be just this thing here would stay the same. So it is w over EA multiplied with x squared over 2 minus w L squared divided by 2 EA. All right, so this is the exact expression for the displacement. Now, if you want to go back and draw the displacement, I said if you have a constant force, which if you have a fixed force at the free end, the displacement is just going to change like a line here. Whereas if you have this type of forces, I'll just draw it here one more time. So you have the cantilever, you have the forces uniformly distributed. Then in this case, the displacement here is going to look like a parabola. So this is a quadratic function. This is a second order polynomial. So the displacement field would look like this. I'll probably just draw it here. So at this free end, I'm using the expression at this free end. So you have x is equal to 0 at the free end. So x is equal to 0. This will give us u is equal to minus w squared divided by 2EA. So this is the value at x equal to 0. And at x equal to L, we know that u is equal to 0 anyway. I mean, you can substitute L in there. So this is going to cancel together, and u is equal to 0. So u basically is changing between minus w L squared over 2 EA to 0. So here, minus 2 w, w L squared over 2 EA. So this is the value of u here, and it gets back to 0 here. Now, in between, it varies like a parabola. All right, so the value of this, or the displacement field in between the 2 points, would look like a parabola. Now, if you want to interpolate this using a line, this is the best you can do. You can get the first point, you can get the last point. In between, you will miss the displacement by a certain amount. Whereas if you interpolate it using 2 elements instead of 1, you will get again this point. I'll just use a different color. You will get again this point, you'll get this point, you'll get this point. And this is going to do a good job relatively. So it's going to match it, but it is not going to be the exact thing. However, if you look into the stresses or the strains, again, the relation between the strain and the displacement is just going to be the derivative. And the strain is the derivative of u with respect to x. You already have an expression. You already have an expression for the strain, and this is exactly the same expression you have for the stress, just divided by just multiplied by the elasticity modulus. So if you want to look into how the stress would look like, which is quite important here. So the stress is varying between 0. So at x is equal to 0, you will have the stress to be equal to 0. And then at x is equal to L, you will have the maximum value for the stress. So sigma is going to be WL over E. Sorry, this is the stress, so it is divided by 8. Oops. So the stress in this case is varying between 0 and the maximum number. So this is 0, and this is WL over A. So this is the maximum number. Now, the strain is the derivative of the displacement, and the stress basically is obtained in the same way. If the displacements are interpolated in a linear way, the derivative of a linear function is a constant. So the displacement would look like a line equation, ax plus b. The derivative of the displacement is just going to be a. So in this case, it's going to be a, right? So if you are interpolating the displacement with a line, you would be in fact interpolating the displacement, or so you will be in fact interpolating the stresses using a constant. And this would be the constant you get. So in this case, you would be missing the stress quite significantly. If you get into two lines, you would be interpolating using two lines instead of, so two constants instead of one constant. So this would be the two constants you are going to use, and you'd be missing the stress by this amount. Now, this is a lot larger than the amount of the displacement. So you miss the displacement significantly. The amount of displacement you miss is a lot less significant compared to the amount of the stress that you miss. Now, we discussed this in the past when we solved this example. If you remember, I'll probably just share. Yeah, I should probably share my presentation here. If you remember when we solved this example here, where we have a uniformly distributed load, in this case, we solved this problem twice, once using one element, and using one element, we have this value for the displacement and this value for the stress. If we use two elements instead of using one element, we get this value for the displacement and this value for the stress. Yeah, here, this is the value for the stress. So this is the value we get for the stress. If you remember that. And we said that this is the amount of the stress you would be missing in case of using two elements instead of one element. Now, I've summarized this here. And this is the solutions we get. Now, if you go back and see the displacement we have, you'll see that the displacement at this free end is WL squared over 2EA. I'm just going to write them here. Or probably just move the entire expression for the displacement. So this expression here, I'm just going to copy that to the new screen. Oops. So if you look into this expression here, at u or at x is equal to 0, now you need to be careful because here x is starting at this end, whereas in this analytical solution, we have x is starting here. So the numbers should be negative. So first of all, the amplitude of the displacement should be negative, and you need to be careful that L is starting or x is starting here in the analytical solution, whereas in the finite element solution, x is starting at this end. So you just need to be careful how you convert between the coordinate system, how you look into the two coordinate system. Okay, so I'm going to call this x bar just to simplify things slightly. So this is x bar and this is x bar. All right, so at x bar is equal to 0, you have this expression is equal to minus WL squared over 2EA, and the displacement is exactly this number here, and is exactly this number here. So this is exact, this is absolutely correct. If you look into at x now, if you want to find the exact displacement at the mid-length, at x bar equal to L over 2. Now, obviously, you have the negative sign here. You don't have the negative sign in there because we're talking about the opposite direction. Now, if you look into x bar equal to L over 2, so this will give you u is equal to, this is just substituted by L over 2. So it is going to be W L squared over 2 multiplied with half, and then you have EA minus WL squared over 2EA. So this is basically 1/4. So it is going to be WL squared over 4EA. And I'm subtracting half from that. Now half is basically 2 divided by 4. So I'm just going to replace this by 4. 4 multiplied with 2, though this is 8. Oops. And then you want to subtract half from 1 over 8. So this is going to be then 4 divided by 8. So it is minus 4 plus 1 is going to be minus, oops, just move a little bit lower. So then this is going to be minus 3 over 8 WL squared over EA. And if you look into the value of delta 2, this is the value at node 2, this is mid-length, is 3 over 8 WL squared over EA. So this is the exact one. Whereas if you look into the stresses, just like I said, the exact stress is varying in a linear way, whereas the value of the stress you get from the finite element method is basically constant. So you get constant numbers in there. And this would miss the stress by quite a significant bit. Now, by the way, when I solved this example, I've asked you what number of elements I would need in order to get a 0. Or probably 1% error. Now, if you look into this error here, this error is 25%. Here you are missing the maximum value of the stress by 1/4. So this is 25%. So what would be the value, or what would be the number of elements in order to get a 1% error? Anyone has been able to figure this out? Applying that is, if you can think about some sort of a relation, develop some kind of a relation between the number of elements and the error you get. Now, there is a branch in mathematics, and the mathematicians who would study the finite element method, they developed a completely new branch, and some people are spending their life working on that branch. This is called the error estimator, and they have 2 types of error estimate, the priori error estimate and the posteriori error estimates. And in this case, they have some types of error estimates that can tell you the error before you solve the problem, and some type of, and remember, this is not quite a trivial problem because we are talking about any type of problems where you don't have an exact solution. I mean, the example of the skull we discussed in the first lecture, you don't have any exact solution for that. So it will be very useful if someone can give you an expression that can estimate the amount of error you are making in there. Okay, so this branch of mathematics I'm talking about is called the error estimates, and they can develop expressions for estimating the error. So I want you to have some sort of a think about that. I mean, this is what I wanted you to do when we discussed this example some time ago. And in reality, it is, yes, it is 50 elements. So basically, you need 50 elements to be able to get 1% error in the exact solution. And if you basically, I mean, you can think about this in different ways, and you can split it into smaller and smaller parts. So each part would be related to the size of the error you're missing. And if you think about it in this way, you will be able to find some sort of a relation, so you can estimate exactly what would be the error for a certain number of elements. Okay, so the number is 50 elements in estimating the error, and you need to have 50 elements. Now think about it, 50 elements. So you need to have 51 equations to solve in order to be able to get 1% error. This is a lot of elements. So 50 equations to solve is going to be probably something also for the computer to be spending time on, or probably in your case, you are going to need a lot of time to solve 50 equations. So the alternative to that, instead of trying to do that, how about doing an alternative approach? See, in this case, probably just to draw it one more time, it quite easily gets very messy. So this is the problem we are trying to solve. And this is how the displacement would look like. And this is how the stress, so this is U, and this is how the stress would look like. And by the way, the stress and the strain would look like this type of figure. So both of them are related. And if you look into the parabola, that the stress or the strain is the rate of change in the displacement. And if you look into the parabola, you'll see that the derivative of the parabola at this point is 0. So this is why you have 0 value for the stress. And then the derivative of the parabola is maximum at this point, and this is why you have the maximum value for the stress at this point. So if you look into the rate of change into this curve, you'll see that the rate of change will correspond exactly to the plot of the stress. Again, just like a rate of change. And again, this is very similar to the relation between the displacement and the velocity. All right, so we are trying to interpolate this with shape functions n1 and n2 that would use lines to interpolate the displacement. So trying to use lines to interpolate the parabola, and is going to use constant to interpolate the stress. So it's going to use constant for that. Now, how about instead of using lines to interpolate a parabola, how about using a parabola to interpolate a parabola as a second order interpolation for the parabola? So instead of using these lines, instead of using lines, how about we use parabola to interpolate it? And then the derivative of the parabola is going to be a line. And then the parabola can capture the parabola exactly. And the line variation can capture the stress variation exactly. Can we do that? What do you think? When we are solving this problem, we know that the displacement would look like a parabola, and we know the stress is going to look like a line variation. We're talking about a uniformly distributed force. When using the finite element we have been working on so far, so this is the linear element we have developed, we know that the shape functions would look like a line, and the derivative of a line is going to be constant. So this element we have in here is going to try and interpolate the parabola using a line. So something like this. And then it's going to try and interpolate the stresses with a constant. So this is not quite a constant. I probably just draw it with a constant. We'll try to interpolate this using a constant. Now, this will result into a huge error in the stress, not very bad error in the displacement, but into the stress, you produce quite a lot of rubbish if you want. I mean, I would describe this results as rubbish. So, alternatively, if we can use a parabola to interpolate this, so instead of using a line, how about using a parabola? And then the derivative of the parabola is going to be a line, and we can capture things exactly. Don't you think that this is a possibility? Or do you think we can do that? Or if we can do that, how do you think we can do it? Yes. So instead of using a linear element, we just use a quadratic element. So if you remember, for this element, the equation we used originally for u is ax plus b. I probably just go back to the presentation. Oops. So if you look into the equation we used, it was this one. And this is an equation for a line. So instead of using an equation for a line, how about using an equation for a parabola? a2x plus a3x squared. You come here. Yeah. If you come here, instead of using this equation, u is equal to ax plus b, how about we use... Yeah, my screen keeps jumping into the wrong place. How about we use u is equal to ax squared plus bx plus c. So instead of using a line equation, we use a parabola equation. Now, if we use the parabola equation, we can capture this variation exactly. And then the derivative of the parabola equation is going to be a line equation. So the derivative of this equation is going to be 2ax plus b, which is a line equation. And the line equation can capture the exact amount of the stress. So this would be a lot more efficient than using lines or many lines. See, in one element, which has this type of expression or this type of approximation, one element would be able to capture this exactly. And we are talking about zero error here. Whereas in this case, if we want to get 1% error, we're talking about 50 elements. So instead of using just 50 elements, you can use one element and get the exact solution. So see how efficient is that? This is quite an efficient way to capture the solution. So this pretty much was the introduction for the lecture today. It was quite a lengthy introduction. And this is why we are going to use quadratic elements. So what we are going to discuss today is quadratic elements. So this type of elements. Obviously, before we had u is equal to ax plus b. So our element had two nodes. When we're talking about u is equal to ax squared plus bx plus c, we have three unknowns. So we should be talking now about three nodes. So it is not two-noded element anymore. It should be a three-noded element. Okay, so I'm just going to derive the shape functions for this element just the same way like we did in the previous element. Okay, so first of all, I'm just going to rewrite the expression we had for the two-noded element, just to remind you of that. And then I'm going to show you how these expressions would be exactly the same expressions once we move into the quadratic element. So these expressions can be written here. So for u, we have n1, n2 multiplied by u1 and u2. And then we have the strain is the derivative of the displacement, or the strain is the B matrix multiplied by the displacement matrix. Probably just make it slightly. I mean, this is the matrix. I'm just going to write it in detail. If you remember, we had this minus 1 over L, 1 over L, multiplied by U1 and U2. And of course, you have the stress to be the elasticity modulus multiplied by the strain. I'm just going to add the expression which we used only once so far. This is the expression we used for the stiffness matrix. If you remember, the stiffness matrix was equal to A multiplied, I probably just write, since we've done this a while back, I'm just going to write the whole thing. So integral over the volume for the B matrix, transpose multiplied with the D matrix, multiplied by the B matrix, integrated over the volume. We said that we are talking about a line, that the cross-section of this line is constant. And then in this case, we can change the integral over the volume to an integral over the length. So it is the integral over the length and dx, and we just multiply by the cross-section. And the B matrix here, so probably the D matrix first. The D matrix is basically, we're talking about a linear element which has only a material property of elasticity modulus. So this D matrix here is just the elasticity modulus. So we can take it out and put it in here. So the stiffness matrix is basically integration over the length. The length is going between 0 and L. For the B transpose multiplied with the B over X. So this is the expression we had for the stiffness matrix. We're still talking about a constant cross-section. We're still talking about the same material properties. We're still talking about the length L. So these properties all are the same. So this expression for the stiffness matrix will be sufficient for us to use for the new element as well. Okay, so I'm just going to write this B matrix. I mean, this B matrix, if you remember that, is the derivative of the displacement. And since the displacement are now written in terms of N1 and N2, so the B matrix is just going to be the derivative of N1 with respect to X and derivative of N2 with respect to X. And you remember the expression we have for N1 is just going to be X2 minus X divided by X2 minus X1, and N2, it was X minus X1. So sorry, it is X by S, it is correct. X minus X1 divided by X2 minus X1. And the derivative of N1 with respect to X is, I mean, this is constant, this is constant, this is constant, is only minus X. So it's going to be minus 1 divided by X2 minus X1. And the derivative of this one, this is the only X in there, this is the only variable in there. So it is 1 over X2 minus X1. And X2 minus X1 is basically the length. So it's equal to L. So this is equal to L. And this is the expression we have for the B matrix. So it is minus 1 over L, 1 over L. So this is the B matrix. We have used the B matrix only once to derive the stiffness matrix, and we are going to use it again today. All right, so this is just a mess of expression. I'm just going to remove things which you are not going to need today. So I'm just going to, just going to remove these. I don't think we are going to use them just now. Just delete these guys. And I probably just, probably just remove this one as well. This one. I'll probably just remove this one and rewrite it in a neater way. Okay, so the B matrix is the derivative of N1 with respect to X and the derivative of N2 with respect to X. Okay, so what we need to do for this new element here, we need to find the shape functions. we need to find the B matrix, we need to find the stiffness matrix. So this is the three things we are looking for. I'm going to just highlight them here. The shape functions, the B matrix, and the stiffness matrix. So this is a matrix. I'm just going to write it as a matrix. If we have these three things, we can solve this problem where we have a uniformly distributed load. We can solve it exactly and get the exact solution using one element. Okay, first of all, I'm just going to make these suitable for a three-noded element. So first of all, I'm just going to write this for 3 nodes instead of 2 nodes. So U is going to be N1, N2, and N3 multiplied by U1, U2, and U3. So this is the first thing. The strain is still the derivative of the displacement and still the B matrix multiplied by U. But now the B matrix is the derivative of 3 shape functions. It's not just 2 shape functions. So the B matrix is going to be the derivative of N1 with respect to X, the derivative of N2 with respect to X, the derivative of N3 with respect to X. And then this needs to be written like a matrix. And then, of course, this is not going to be like that. So I'm going to remove this for the time being. Once we have the B matrix, I'm just going to rewrite it. And then we have the stiffness matrix. The expression for the stiffness matrix is still correct. Instead of using 2 entries in the past for the B matrix, we are going to use 3 entries in this case. All right, so first of all, let us find the shape functions, N1, N2, and N3, and then we can worry about the B matrix and we can worry about the stiffness matrix. So I'm just going to probably just derive it here. I'm going to move this one to here so that we can work. All right, so the expression we have for the displacement now is U equal to A x squared plus B x plus C. We know at the node number 1, we have the displacement equal to 1. At node number 2, the displacement is equal to U2. And at node number 3, the displacement is equal to U3. At U1, we have x is equal to 0. At U2, we have x is equal to L over 2. At the third node, we have x is equal to L. Just like we did in the past, we are going to repeat the same procedure to derive the shape. So this procedure I'm using to derive the shape function is exactly the same procedure you would be using universally for any type of element for any number of dimensions. So this procedure would work for quadratic element, for cubic elements, for any type of elements if you wish, and it will work for elements in 1 dimension, line elements, or it's going to work for elements in 2 dimensions, triangular elements, quadrilateral elements, or if we talk about 3 dimensions, it's going to work for hexahedral elements, tetrahedral elements, it's going to work pretty much for any of them. Okay, so it is the exact same procedure. I'm going to repeat it one more time. I've done this first for the linear element, and then I did it again when I found the shape functions for the 2-noded elements. I'm going to do it the 3rd time now. Okay, so at x is equal to 0, we have U is equal to U1, and then I'm going to substitute the x in here. So it is A 0 squared plus B 0 plus C. Now from the first equation, we immediately have C is equal to U1. And I'm going to use that in the following 2 equations. I just don't want to repeat writing C. At x is equal to L over 2, we have U is equal to U2, and this is equal to A multiplied with L over 2 squared plus B multiplied with L over 2 plus U1. I have this to be C, but I'm just replacing it immediately with U1. Okay, so I'm just going to rewrite this equation. It is U2 equal to A L squared over 4 plus B L over 2 plus U1. Now this is my second equation. And then at x is equal to L, you have U to be equal to U3, and this is equal to A multiplied by L squared plus B multiplied by L plus C. C is U1. So this is my second equation. Forget about, this is my third equation if you want, but if you want to solve for A and B, you have two equations, equation number 1 and equation number 2. Now this is two equations with two unknowns. The unknowns here are A and B, and I'm going to assume that everything else is known. I'm going to assume that U1 and U2 are known for me, are information that I already have. Okay, U1, U2, and U3. So I'm going to solve for A and B. Two equations, two unknown, though this should be easy to solve. I'm going to take this equation first. Oops. And then I'm going to take this one second and trying to solve them. All right, so I'm going to use it. I'm going to solve it by substitution. I want to cancel one of these terms to have the other one. I want to cancel A or B, so I have the other one. I'll just use black again. So I can multiply this equation with -2. This will be minus BL plus BL is going to cancel together, and then I'm going to add the two equations. So multiplying this second equation with -2, I will have minus 2U2. Instead of 4 here, I will have 2. And instead of half, so I need to add the negative signs as well. So this is minus there. And then I have minus 2U1. I want to add both equations. I have on this end U3 minus 2U2. This is equal to half A subtracted from A is going to be A over 2L squared, and B plus B minus will cancel together. I'll be left minus 2U1 will be leaving me with U1. Negative, sorry, it's not positive. Now to find the value of A2, to find the value of A2, I'm just going to take this to the other end and multiply it by 2 and divide it by L. So this is going to be L squared equal to U3 minus 2U2 plus U1, and then multiply the whole thing by 2 and divide the whole thing by L squared. Come on. And this is the expression I have for A. All right. Now I can use this expression, put it back into equation number 1 or equation number 2, and get the value of B. So I'm just going to insert it into this expression for U3. So I will have U3 is equal to A. I have a value for A now. So it is U3 minus 2U2 plus U1, 2 over L squared. This A here is multiplied by L squared, so I'm just going to multiply it by L squared plus B multiplied by L plus U1. Now, the only unknown for me in this equation is going to be the B. L squared will cancel away with the L squared, so I'm just going to remove them. Remove these guys as well. And then I have 2 to be multiplied by U3 and U2 and U1. So this will, I will just multiply them and move them to the other end. So it is U3 is equal to 2U3 minus 4U2 plus 2U1 plus BL plus u1. u1 added to u1, this will make it 3u1. Just remove this. And then I moved everything to this end here, is going to change sign and move to the other side. So this is plus, this is minus, this is minus, and this is equal to BL minus 3 U1 plus 4 U2, and we have U3 minus 2 U3, so this is going to leave us with 1 U3. This is the negative 1 U3. Just write it there. So this is minus U3, and I can just divide the whole thing by L. And we have the expression for B. So we have the expression for A, and we have an expression for B. I need to go back and insert them into this mother equation in there. Where's that? Oops. Yeah, to this equation here. I need to insert the value of A and B in here. I'm just going to move that next to A and B, so it is easier to see things. I'm just going to copy A here as well. So I'm just going to insert these guys into the equation number or equation star. Inserted here and inserted here. You will have U is equal to A, U3 minus 2 U2 plus U1 L squared, or it's 2 over L squared, multiplied by X squared, obviously, plus B, I have minus U3 plus 4 U2 minus 3 U1 multiplied by 1 over L multiplied by X. And then you have C, this is U1. You already had C from the first equation. So this is the equation I have for the shape functions. I only need to arrange things so that I have everything to do with U1 first. This is U1, this is U1, and this is U1. And everything that is multiplied by U1 is going to be my first shape function. And then I take everything to do with U2 second. So this is U2, this is U2. And then everything has to do with U2 is going to be the second shape function. And finally, I have the things that are multiplied by U3. So it's going to be my third shape function. Okay, so I'm just going to take this order. So U is equal to U1. I have U1 multiplied by 2 over L squared X, L squared X squared U1. And then I have minus 3, 1 over L X. So it is minus 3 L X and U1. And then you have U1 on its own. So this is everything to do with U1 came first. And then I have things to do with U2. So first of all, I have minus 2 and 2. So this is going to be minus 4 L squared X squared U2. And then I have 4 U2 multiplied with 1 over L X. So it is plus 4 X over L U2. And then finally, so this is going to be my second shape function. And the final thing, I have U3. I need to probably just move a little bit here so I can still see U3. So in the first equation, I have U3 2L squared, 2L squared, X squared, U3. And then from the second equation, I have minus U3 multiplied with 1 over L X. So this is going to be minus 1 over L X U3. And this is going to be my third shape function. So this is the three shape functions I'm going to have. I'm just going to take u1 as a common factor in the first equation, and u2 is the common factor in the second part, and u3 is the third part. So u is going to be 2 over L squared x squared minus 3 over L x plus 1. The whole thing is multiplied by u1. Then I have added to minus 4 over L squared x squared plus 4 over L x is multiplied by u2. And then I have 2 over L squared x squared minus 1 over L x multiplied by u3. So you remember the expression we have for the shape functions and the relation with the displacement is that, this one here. So this is the guy we are looking for. So I'm just going to rewrite it here below. Is a lengthy one. So u is going to be this guy here. I'm going to call it n1. And this guy here is my n2. And this guy here is my n3. So I'm just going to write them down. So this is n1, n2, n3 multiplied by u1, u2, and u3, where my n1 is equal to 2 over L squared x minus 3 over L x plus 1. n2 is equal to minus 4 over L squared x squared plus 4 over L x. And then n3 is basically 2 over L squared x squared minus 1 over L x. So this is the expressions I have for my n3. N3, N2, and N1.